Okay, welcome back for our second installment here in Chapter 3. So hopefully you were able to get used to those element symbols and names, and now we'll be ready to move forward into the periodic table. Alright, so the periodic table, you've seen it and hopefully used it in the past, but at least you've seen it. Anywhere where the movie or television show wants to portray a scientist, they do one of two things. Either they toss a periodic table in the background, or they put the person in a lab coat, or most often they do both those things. So the periodic table is out there, whether or not you've ever made much use of it. So we're going to look at how those element symbols that we just talked about and how the layout of the periodic table using those element symbols will be helpful to our understanding of chemistry, not only in this course, but for those who go on in another chemistry course, such as 142, for instance, will certainly be making use of the periodic table there as well. And there we have it, our beautiful, glorious periodic table of the elements. Notice this one has color-coded. We've got a few different colors there. All those blue elements, over 2/3 of the known elements are blue on this table because that indicates that they're metals. So most elements are metals in their elemental state. Then we have that green staircase that sort of separates the metals and the nonmetals. Aside from hydrogen there way at the left top, that doesn't really fit there. It doesn't really fit above fluorine either. It sort of has properties of both. So it's a loner element that's out of place, but we stick it there at the top of group 1 for reasons we'll talk about later. But that hydrogen and the other yellow elements there are the nonmetals, and that staircase I just mentioned, the metalloids or semi-metals, those are sort of transitional type elements. They have properties of metals and nonmetals, and that's why silicon that we see there, number 14, the second member of our staircase, is our important semiconductor material for use in computing, because it conducts like a metal does, but it doesn't conduct very well, so it's more like a nonmetal in that regard. So it's sort of intermediate conductivity, and we can dope it, we can cause it to have tunable conductivity, and that's why we use silicon, our second most abundant element on Earth, at the heart of our computer chips. Okay, so there you have it, mostly metals, some nonmetals, and then our staircase to separate. Okay, so looking in the periodic table, in addition to just separating our elements by type, either metal, nonmetal, or metalloid, or semi-metal, we have also the groups. So groups are the vertical columns in the table, and they're ordered from left to right, and within a group, you tend to have similar chemical properties. Aside from hydrogen being very different from the other members of that first group, typically you have similar chemical and physical properties among those groups. They're often called families because of their similarities, but group is what we call the vertical column. Periods are those horizontal rows. So period 1 would involve just hydrogen and helium, and then period 2 we get 8 elements total, and then we move to even more elements once we get down to period 4 is where we start to see the transition elements, even though they actually are filling orbitals in the 3rd energy level. But we'll save that discussion for later. But we have currently in our table 7 complete periods, at least complete in the way that we represent our table. And so here we see a graphic that highlights group 2, so that second vertical column, so the groups we count from left to right, and then it also happens to highlight period 4, where we see the first group of the transition elements there after potassium and calcium, and then we end with the Nobel Gases, which are at the extreme right end of the table. We have that little area tucked down at the bottom, the rare earth elements, lanthanide and actinide series. We won't talk a whole lot about those in this course or in 142, but they are important for a lot of the technology that we use today, and they're tucked down there for reasons we will discuss when we get to a later chapter. So a little more about those group numbers. We already mentioned that the groups themselves are the vertical columns from left to right. The group numbers, we have a couple of different numbering systems. So we tend to use a number and a letter for the elements. So for those first 2 and last 6 columns, we tend to use the letter A. We call those representative elements. So we have 1A to 8A, and we skip over the middle there. The transition elements, we tend to use the letter B for those intervening 10 groups. The representative elements, as I said, include the first 2 groups, so group 1 or 1A and group 2 or 2A, and then also groups 3A through 8A, which, if you're counting the 10 groups of transition metals, then you would skip from 2 to 13, and then 14, 15, 16, 17, 18, or we would just pick up with 3A, 4A, so on and so forth. We tend to prefer, nowadays, actually, just the Arabic numerals with no letters. So you'll more commonly see the last group, the Nobel Gases, referred to as group 18 instead of group 8A. The A and B nomenclature was more popular several decades ago. We've moved away from that in recent years. All right, so let's talk about the groups. In particular, let's talk about the alkali metals, group 1A or group 1. And this would, again, exclude hydrogen, which is in that group but doesn't really belong there because it's not a metal. All the rest of the group 1 or 1A elements are metals. And so if we're excluding hydrogen, we'd start with lithium, would be the topmost element that we include in the alkali metals because it's the first metal element in that family. And then we move down to cesium. And a couple of things to note, these substances all tend to be silvery metallic substances, elements that differ in reactivity as you go down. They get more and more reactive. So all of them will react with water, for instance, to generate hydrogen gas and form their hydroxide, but lithium won't be nearly as violent as sodium or potassium. As we keep going down, the reaction with water, for instance, is much more violent, but they all share that chemical property of being water reactive. So they are family members in that regard. And just like your family, they're different. Each member is unique, but they have similarities. So let's skip almost to the very last column, skip to the second to last column, group 7A or group 17, the halogens. This would include the entire vertical column there, fluorine down through astatine. And again, they are similar in their chemistry, but it's the exact opposite. Whereas the lower you went in group 1 or 1A, the more reactive you got. The halogens, which are nonmetals, the higher you are, the more the reactivity. So fluorine, the highest member of that group, is actually the most reactive, and then reactivity decreases as you go down. And that's the big difference between metals and nonmetals when we do chemistry. Chemical reactions involving metal elements, the metal element tends to lose electrons, and it's easier to lose electrons down at the bottom where you're larger and you have more electrons to keep track of anyway. Nonmetals tend to do their chemistry by gaining electrons, and that's easier to do if you're a small element that doesn't have so many electrons, and that's why we see the opposite trends. Halogens, which are nonmetals, the reactivity is greatest at the top, and they get less reactive as you go down. The alkali metals that we just talked about, being metals, they tend to lose electrons in their chemical reaction, and therefore those elements get more reactive as you go down. More electrons in those larger elements, the further from the nucleus, easier to lose. Finally, our very last vertical column, group 8A or group 18, is the Nobel Gases. And we call them noble not because they fight dragons and save princesses, but rather because they are relatively inert, chemically speaking. They don't react very much. They're among the least interesting for us in that regard, although some of the lower members of that group, krypton, xenon, and radon, for instance, can be forced into chemistry with a reactive element like fluorine that we just talked about in the halogens. But ordinarily, they don't do a whole lot of chemistry, and that's where they get the name noble or inert gases, they're sometimes called. So in nature, we don't find them chemically combined. They tend to stay as the pure elements. They were actually very tough to discover because they don't do a lot of chemistry and they're gases, so they're not very easy to see or to discover by chemical methods. So it took a while before we discovered the Nobel Gases because we didn't know what to look for. And then finally, when doing work with other gases, we were able to discover that there were these additional noble gases, elemental gases, that don't do much chemistry and aren't usually combined with other elements aside from fluorine or oxygen for some of those lower members under very special conditions in the lab. Okay, so we've come to that point where we should probably check in and see how you're doing. So here's our first learning check for this subtopic. And the goal here is to identify the element described by the following information. So for number 1, we're looking for an element in group 7A or 17 that appears in period 4. For number 2, we're looking for the element in group 2A or group 2 that occurs in period 3. And then finally, the address there for the third element we're looking for is group 5A or 15 and period 2. So we're looking over and down according to the vertical group number and the horizontal period for the horizontal row. All right, so if you haven't already determined those, go ahead. You should have that periodic table that's posted on Blackboard for your use, and identify those elements. Pause the video if you must, and we'll see how you did. Okay, so if we're in group 7A or 17, we're dealing with the halogens, the second to last column, and if we go down 4 periods, we're looking at A. Bromine is the element described by that address, by that set of conditions of group and period number. For number 2, group 2A or group 2 period 3, we're looking at B. Magnesium. And then the third example here, group 5A or group 15 period 2, we're looking at C. Nitrogen. So hopefully that was pretty easy for you. If not, go back and make sure that you understand it now. It's not a very difficult thing, but it does take a little getting used to. So if you struggled with this learning check, go back, see if these solutions make sense. If they don't, certainly reach out, send me an email, get in touch with me so that I can help clarify any problems. Okay, going back to that early graphic, metals, nonmetals, and metalloids, we already talked about these 3 major classifications of elements, and again, that heavy zigzag line there, as they call it here in the slide, that sort of greenish that separates the blue and the yellow, those are metalloids, or semi-metals as they're sometimes called. So the metals, they're blue and they tend to be over to the left, aside from hydrogen that's way at the top of group 1. The nonmetals, which are depicted here as yellow, they tend to be up and to the right, and also hydrogen. And then finally, the metalloids are that staircase that separate the metals and the nonmetals, and they have intermediate properties, sometimes more like metals, sometimes more like nonmetals in their chemical and physical properties. Speaking of those physical properties anyway, metals tend to be shiny and ductile. They can be drawn into wire is what that second term means. So you often see metal wire, copper wire, for instance. They are usually good conductors of heat and electricity. That's another key property of metals. Nonmetals, on the other hand, are typically not especially shiny. They're not usually ductile or malleable. Usually they're much more brittle. So you can't pound them into sheets, which is what malleable means. You can't draw them into wire, which is what ductile means. But instead, they're fairly brittle and they break up pretty easily. They also tend to be poor conductors of heat and electricity. And then finally, the metalloids are better conductors than nonmetals, but they're not as good as metals. So they're semiconductors, which is great for computing, and that's why initially germanium was explored, and germanium does very well, but it's so rare and expensive that when it was possible to dope silicon and use that instead, that's why silicon is now the element of choice for computing and semiconducting, because it's abundant. Doesn't occur as silicon element. It occurs in mostly sand, silicon dioxide, sand, or quartz, but it is abundant, second most abundant element on Earth, and so being able to use that in semiconducting and insulating, it's a lot less expensive than if we use germanium, which was again initially explored for that application. So there we have the properties of those 3 main types of elements. Okay, if we go ahead and look at table 3.3 from our text, here's a comparison where we have a metal, silver in this case, antimony, a metalloid or semi-metal, and then finally sulfur, a non-metal. And you can go ahead, I'm not going to read it to you, but it talks about the key differences, and they're basically the same things that we just discussed in general, only now you get specific elements with properties compared and contrasted. Alright, this slide, since I know many of you are interested in the health professions, we have a slide here that shows the major elements essential to health. And if we look at those red lines around the key elements, hydrogen, carbon, nitrogen, and oxygen, those are the main ones, right? Especially water. H2O is a key component of your average 60 kilogram adult. The CH, O, and N also are key components of proteins and carbohydrates and other things that people are made of. The macro minerals, things that we need a lot of that again aren't in as huge of quantities as those four we just mentioned. We see things like sodium, potassium, magnesium, calcium, phosphorus, sulfur, chlorine. Those tend to be needed, or at least not harmful to us, in fairly big amounts. And then finally micro minerals, trace elements. We see a number of the transition elements there, and those we do want a little bit. Too much is bad, the wrong form is bad. Chromium, for instance, as a +6 ion can be harmful, carcinogenic, but as a +3 ion, it's necessary for things like insulin to be manufactured and used correctly. So we have a number of elements that we're aware of that we need very small amounts of. Microminerals, they're called your trace elements, and we're not entirely sure that that's it. There may be more discoveries later on, but these are the ones that as of now we expect or know that they have need in human health. But again, the dose makes the poison. Be careful. Too much of any of them is not a good thing, especially those micronutrients, microminerals. Alright, let's pause again for a learning check here, and this time we're going to see how well you're doing with that idea of metal, non-metal, or metalloid. So we have 5 elements here, and you'll just identify them if it's either a metal, a non-metal, or a metalloid, or semi-metal as they're called. So number 1, sodium, 2, chlorine, 3, silicon, 4, iron, and 5, carbon. Go ahead and jot down whether each of those is a metal, a non-metal, or a metalloid. Pause the video if you still haven't made your determination, and when we pick back up, we'll see how you did. Okay, so sodium, which is in group 1, way over to the left, so it should be a metal. Hopefully you correctly identified it as such. Chlorine, way over in group 17 or 7A, almost at the end of the table, so that's a non-metal. Silicon, we have mentioned that quite a bit. It's right on that diagonal, and it's a metalloid. Iron in the transition metals obviously is a metal, and carbon, which is on the right of our staircase just after boron, is a non-metal. So hopefully that went well for you, and we're going to go ahead with another learning check now. Okay, so before we close our chapter, we've got one more learning check here, or at least close this sub-chapter. For this learning check, match the elements to the description. So number 1, we're looking for metals in group 4A or group 14. And so you see the choices. I won't read them all to you, but we're looking for just the metals there in that group. Number 2, we're looking for the non-metals in group 5A or group 15. So you see the answer choices there, and we're looking now just for the non-metals. Number 3, the metalloids in group 4A or group 14. So again, just the metalloids or semi-metals for that one. Pause the video if you still need another moment, and then start back up and we'll see how you did. Okay, so here we have it. The metals in group 4A or group 14 are tin and lead, right? Germanium is a metalloid or a semi-metal, as is silicon, and then carbon's a non-metal. So that looking for the metals, we're looking down beyond the staircase. Number 2, for the non-metals in group 5A, now we're looking up above that staircase, and that leaves us with choice B, nitrogen and phosphorus. And then finally, back to group 4A or 14, we're looking now for the metalloids, and that's one where we have 2 metalloids, silicon and germanium, and hopefully you remember the discussion about germanium as a semiconductor being displaced by silicon, so that hopefully was in your mind when you were making that selection. And again, not always do we have two metalloids in a given group, and not always in a group 1 and 2, we have no metalloids. So be careful about that, but this time silicon and germanium. So hopefully you had very little trouble, if any, with any of our learning checks. Hopefully this is all making sense and meshing well with your understanding. If that's not the case, certainly get in touch with me. Otherwise, we'll see you for the next part of Chapter 3.